Welcome back to Summarize Science. Think about a typical drone. It's fast, agile, and built on a stiff, rigid frame. But what happens if it bumps into something? Usually, it's game over. Now, a new research paper introduces a design that turns this limitation on its head. They call it the FlexiQuad, a quadrotor inspired by the incredible capabilities of natural flyers like birds and insects. The key is a flexible, ring-shaped frame that mimics the anisotropic stiffness of animal wings, meaning it's stiff in the directions needed for flight, but compliant in others. Another clever idea is distributing the mass, like batteries in motors, around the frame instead of lumping it in the center. This avoids the wobbliness you'd expect from putting a heavy payload on a soft structure. This unique design unlocks some incredible and previously contradictory abilities. First up is squeezability. The frame can actively compress, allowing the drone to fly through gaps as narrow as 70% of its normal width. The researchers demonstrated this with a controlled squeeze-and-fly maneuver through a narrow opening. Second, and perhaps most impressive, is collision resilience. While a conventional drone would likely shatter, the FlexiQuad can slam head-on into a wall at 5 meters per second, or about 11 miles per hour, without damage. It simply deforms to absorb the kinetic energy over a longer period of time. In glancing collisions with its propellers, it reduces the destabilizing forces by an incredible factor of 39 compared to a rigid drone. Now, you might think all this softness would make it slow and sluggish. That's the third surprising feature, agility. Despite being 3 orders of magnitude more flexible than a normal quadrotor, the FlexiQuad is still incredibly fast and acrobatic. It can reach speeds over 80 kilometers per hour and pull off aggressive maneuvers just like its rigid counterparts. The analysis identified an optimal range of softness for the frame. This Goldilocks zone is where the drone gets all 3 benefits without major trade-offs. Interestingly, this optimal stiffness range is very similar to what's found in the wings of real birds and insects. So let's recap the key breakthroughs here. The FlexiQuad design successfully combines high-speed agility, the ability to squeeze through tight spaces, and incredible resilience to collisions. These are 3 properties that were previously seen as mutually exclusive in drone design. So, what does this mean for the future? Imagine drones that can navigate cluttered disaster zones for search and rescue, or inspect complex industrial machinery from the inside, without fear of a mission-ending crash. This research is a huge step towards creating drones that are less like fragile machines and more like the robust, adaptable flyers we see in nature. Thanks for tuning in to Summarize Science.